Because once we have the appropriate function, the calculator is going to do most of the work. Right? Assuming that you've officially bought into the whole, I'm going to use my calculator now because I won't always be able to use my calculator ideology. Right? So the base of solid S is the region enclosed by the graph. So and if the cross section is perpendicular to the x-axis or equilateral triangles, find the volume of the solid. All right. So a picture tends to help. I'll draw one as it would be in 2 dimensions, and then we'll scale it to 3 dimensions. All right. So before we get too far ahead of ourselves, you see the function 1 minus x over 2? It looks like it should be harder than it is, but this is really the same as negative 1/2 x plus 1. And the other one, g of x, is really the same as positive 1/2 x minus 1. Right? So it's not a complicated rational function with asymptotes or things like that. It's a line. Right? So the first line has a y-intercept of 1 with a slope of negative 1/2. Right? So down 1 over 2. Draw a line. We want to bound it with the line x equals 0. X equals 0 is the y-axis. So I want this, something like this. I don't need the other part of it because the leftmost part of the graph is the line x equals 0. All right? Oh, I should have done that in a different color. The leftmost part of the graph, the relevant graph, is the line x equals 0. So then my g function has a y-intercept of negative 1, so like right now, and then we have a slope of 1/2, so up 1 over 2, so it's going to put us right now. And so we're looking at something along these lines. So coordinate 2, 0 ends up being the x-intercept. We have y-intercepts at 0, 1 and 0, negative 1. I'm taking note of both x and y values generally when I do stuff like that because sometimes we'll have to integrate with respect to y, sometimes we'll have to integrate with respect to x. All right, so you want to be mindful of all of those things. So what we have here is the base of solid S. Purple. Right here is the base of solid S. So what we're going to have are triangular shaped cross sections jutting out of the paper. Right? But obviously to get a meaningful representation of that, we do a perspective drawing. So let me get my slanted y-axis and my horizontal x-axis. So x, y, mark off the special locations, 1, 1, 2, connect. I'll use the line draw tool because, as we know, I can't draw. Apparently I can't even use the line draw tool either. Alright, so what I need now are cross sections perpendicular to the x-axis that are equilateral triangles. So let me draw an arbitrary rectangle. And I'll do it going both ways. And then I'll show you how we can kind of handle that. All right, coming off of that arbitrary rectangle would be some sort of triangular shaped figure. That's shockingly not the worst drawing I've ever done. Actually, I'm trying to sound modest. I think that's incredible. You did a great job on that one. I think it's the first time we've ever done a great job on it. I think it looks pretty good. All right, so a triangular cross section coming out of the paper. Okay, so the thickness on that triangular cross section, this thickness here is a change in x, so we're looking at something that's dx. All right, so if I can come up with the area, so we need the area of just a face of an equilateral triangle. If we come up with that, we'll be in good shape. Now, there's like, I can think of 3 ways to do it off the top of my head, but I think the most concise way involves Trig. Okay? You can also do it with 30, 60, 90 right triangle relationships, but I answer that with, well, what if it's not a 30, 60, 90 right triangle? What if we're dealing with something other than an equilateral triangle? If that's the case, we need something that's more universal. Right? So let us investigate the trig formula for area of a triangle. Any triangle, which would be 1/2, well, one version of it is 1/2 AB times the sine of C. Right? So let's talk about what that means, because it's been a little while probably since you've seen something like this. If I draw this, will it actually put the 3 inside? Oh, good. So why was there a 3 there? I know it has 3 sides. I can count. Okay. It doesn't trust me. All right. So if I'm going to use this, well, I need an angle, right? Angle C. Well, what's angle C? Well, let me just label the triangle any way I want. So ABC. C. All right. All angles and sides in an equilateral triangle are congruent. So I know that they're all going to be 60 degrees. And we know that because there's 180 degrees in any triangle, right, if you add up all the angles. We also know that all the sides are going to be congruent. All right, so I actually have the angle, so I'm good there. I just don't know what the sides are actually going to be. All right. Now, but one thing I can keep in mind is for an equilateral triangle, we can streamline this a little bit. The area of that equilateral triangle is going to be 1/2. A and B represent sides of the equilateral triangle, but we know all sides are congruent. So let me just change the variable there and call it S squared, right? Because if there are 2 sides that are exactly the same, if I multiply them together, that'd be the same as saying S times S. I could say A times A, I could say B times B, it doesn't matter. I'm just saying some side S, I'm going to square it, times the sine of the angle, which is 60 degrees. So 1/2 times the length of a side squared times what is the sine of 60 degrees? Radical 3/2. Right, so the area of an equilateral triangle, if we clean that up, would be radical 3/4 multiplied by the length of any side squared. Radical 3/4 multiplied by the length of any side raised to the 2nd power. So the big challenge, as it is in most cases, is coming up with the length of a side. Well, probably could figure out this one. This one has coordinates, if we think about the coordinate at this location, of x, I'm just making sure I'm using the right color. X, comma, negative 1/2 x plus 1. All right, because it's x comma y. And the y value for any point along this line would be the expression itself. Right? So if I needed to find a particular coordinate, I might plug in a 1 for x, but to figure out the corresponding y, I'd plug in a 1 to this equation and see what I come up with. Right? So x comma this would end up being the coordinates of that point. Now, the other point down over here would have coordinates of x comma, I don't want to do in blue. This one over here would have coordinates of x comma 1/2 x minus 1. All right, something to keep in mind. If you're ever looking for the distance between two functions, all you got to do is subtract the functions, dominant minus non-dominant. Right, so this distance here, the one that we're after, this guy, from here to here, is going to be equal to f of x minus g of x. So negative 1/2 x plus 1 minus 1/2 x minus 1. Which is going to simplify down to negative x plus 2. All right, so that's going to be the length of the base of that equilateral triangle. Now, there is another way to do it if you didn't want to work with the entire base. Because we have symmetry here, what you could do is figure out what the volume would be on the top half. So going from the x-axis up, pretending that the bottom isn't there, and then just double that answer. All right, so if you find that to be easier, that's fine. You still need to work with 30, 60, 90, or area of a triangle formula. But this is the length of a side. So what I want to do is integrate on the interval of 0 to 2 for x, because again, we're starting at 0 and going to 2. So 0, 0, 2, 0. Radical 3 over 4 times the length of a side squared dx. The length of a side, again, is negative x plus 2. If you want to make it so it's a little easier to type into the calculator, maybe write it as 2 minus x. All right, these are the same. Switching the order. There's one less operator to write in the calculator. I think it's kind of, after making you do all that, it would be almost mean to make you actually integrate it by hand. You know, isn't this enough work? That's my rationale. I mean, you weren't really questioning too much why I wasn't forcing you to do things by hand, but in case you really needed an explanation, that's it. I mean, this is plenty. In the next unit, the problems will be more standalone. Integrate this, integrate that. Use this technique, use that technique. It won't be, you know, necessarily to meet a particular goal. So it makes sense to ask you to do it by hand in that situation. But we're saying here that we're looking at a volume. So if you can create infinitely many of these triangular regions from beginning to end, and connect them all, you look at some kind of arrowhead looking sort of thing, you would end up with a volume of 1.155 roughly somethings cubed. Feet, yards, doesn't matter. Number 3, well, you know what? Let me just try something. I want to